How can we be sure that there is a square root of 2 in the real numbers? We now apply the completeness property to show that there is. Okay, so we are now going to show that the square root of 2 exists. The theorem says, there exists a positive real number whose square is equal to 2. Let's consider the set S of all positive real numbers whose squares are less than 2. That is, S is equal to X, where X is the element of all real numbers, X is greater than 0, and X squared is less than 2. So S is non-empty and S is bounded above. So we can invoke the axiom of completeness. By the axiom of completeness, S has a least upper bound. Let's call it S. We will see that S has the required property, namely that S squared equals to 2 or S equals the square root of 2. Our plan is to show that neither of the alternatives, S squared less than 2 or S squared greater than 2, is possible. Case 1. S is not an upper bound of S. We will show how to find a positive number t such that t is greater than S and t squared is less than 2, thus contradicting the fact that S is an upper bound of S. Suppose that S squared is less than 2. And let's consider the numbers of the form S plus 1 over n, where n is the element of the positive integers. Let's square such a number. S plus 1 over n squared equals S squared plus 2s times 1n plus 1 over n squared, which is less than or equal to S squared plus 2s times 1 over n plus 1 over n. And that is equivalent to S squared plus 2s plus 1 times 1 over n. Since we're assuming that S squared is less than 2, that means that 2 minus S squared is positive. A result of the Archimedean property says that for every positive real number a, we can find a positive integer n so that 1 over n is less than a. As a result of the Archimedean property, we can choose a particular n so large that 1 over n is less than 2 minus s squared over 2s plus 1. Here, 2 minus s squared is positive and 2s plus 1 is also positive. Let's use the result of the Archimedean property and work with what we had. S plus 1 over n squared is less than or equal to s squared plus 2s plus 1 times 1 over n. and then use our result and substitute s squared plus 2s plus 1 times 2 minus s squared over 2s plus 1, which is equals to 2. If we let t equals s plus 1 over n, then t squared is less than 2. Thus, t is greater than s and t is less than 2. So, s is not an upper bound since s is less than s plus 1 over n. Therefore, s squared less than 2 is not possible. Case 2. S is not the least upper bound of S. We will show how to find a positive number t less than S and t is an upper bound of S, thus contradicting the fact that S is the least upper bound of S. Proof. Suppose that S squared is less than 2. Now, consider the numbers of the form s minus 1 over n, where n is an element of the positive integers. Let's square such a number. S minus 1 over n squared equals s squared minus 2s times 1 over n plus 1 over n squared, which is greater than s squared minus 2s times 1 over n. And since s squared is greater than 2, then s squared minus 2 is positive. Here we use again the fact that for every positive real number, we can find a positive integer n so that 1 over n is less than a. Thus, as a result of the Archimedean property, we choose a particular n so large that 1 over n is less than s squared minus 2 over 2s. Let's remember that s squared minus 2 is positive and 2 times s is also positive. Let's set t equals s minus 1 over n so that t squared is equals to s minus 1 over n squared, which is greater than s squared minus 2s times 1 over n, which is greater than s squared minus 2s times s squared minus 2 over 2s, which is equals to 2. So t squared is greater than 2, which is greater than x squared for all x element of S. And remember that S is equals to x, such as x is the element of all real numbers, x is greater than 0, and x squared is less than 2. But from t squared greater than x squared, it follows that t is greater than x, so t is an upper bound, and because t is less than s is not the least upper bound of S. Thus, s squared is greater than 2 is not possible. Since the alternatives s squared less than 2 and s squared greater than 2 are impossible, we can conclude that s squared is equals to 2. Therefore, s is equals to square root of 2 and the square root of 2 exists.